Hello, we are Ironspace from Carceller, Madrid. My name is Víctor and welcome to our Nanostar presentation. Here is the index that will be followed during the presentation. I am just covering the first and the last sections, whereas my colleagues will be covering the rest of them. The project arises as a necessity of seeking for water on the moon's surface. In order to perform that research, a flyby maneuver is performed with a nanosatellite. Therefore, the main purpose of this project deals with the development of a preliminary design review of that satellite.
Hello, my name is Jorge and I'm going to continue with the presentation. The next section consists on the mission analysis. The first thing is to consider the initial conditions of the mission. It has been assumed that the mission starts at the design GTO of the Ariane 5 launcher, the one used by the ESA. It has a perigee height of 250 km, so drags must be taken into account. It also has an inclination of 6 degrees, so a margin for a plane change must also be considered. The final part of the mission consists on a flyby maneuver with a restricted maximum height of 100 kilometers. It is going to be considered that, when reaching the moon's sphere of influence, a biplane targeting will be performed. That allows to control the flyby height by changing the impact parameter and the hyperbolic speed. Thus, we should include also a margin for this maneuver. The first option to be considered is the electric propulsion. Although it is not energy limited by the energy stored at the chemical bonds of the propellant, it is power limited. In the case of a nanosatellite, the power limitation is more restrictive than in other spacecraft, because the power available is lower than 100 watts. That leaves as the only technology available the field emission electric propulsion. For the simulations, it has been used a model, the IFM nanothruster, which specifications are summarized in this table. To continue with electric propulsion, an optimum specific impulse shall be selected in order to minimize the total mass of the satellite. By looking at the picture, it can be noticed that after 3000 seconds, the mass do not change significatively. So it has been decided to use that value for further calculations. In this slide, the results from the simulation can be seen. The trajectory has a spiral shape, result of the continuous thrust applied during the whole mission duration. Regarding its duration, the mission would last for 3 years approximately, although the propellant required would be low. An additional advantage would be the small size of the system, although an optimization must be performed. The other option is to use chemical propulsion. In this case, the specific impulse is very limited, and the size of the system is larger. The thrust range considered is 1 to 10 newtons. As a first approach, a simple Hohmann transfer with only one barn has been done. The delta V obtained will be used as baseline for the following calculations. The question now is if this maneuver can be considered as impulsive. The answer is no. A preliminary analysis has been made showing that the gravity loss would be very high. Then it has been decided to split the trajectory into several barns, trying to minimize the gravity loss. It has been proven that the optimal would be to use 6 barns, although this would imply an excessive complexity. Additionally, the thrust required to have relatively short burn time must be around 8 newtons. After an iterative process, it has been reached a solution using only 4 barns concentrated at the beginning of the mission and using a maximum of 8 newtons. That would leave a very short transfer time of approximately 10 days and a total delta V, including margins such as drag, of 0.81 km per second. Finally, although it would require a larger satellite, it has been decided to go for the chemical propulsion.
The next section consists on studying by which means the maneuvers explained before are going to be carried out, the propulsion subsystem. An study of the perturbation showed that the most influential one is the drag effect that happens at each perigee crossing. That is why a 5% margin should be left in terms of delta V. It is going to be considered that the ADCS system won't require any propellant mass, so it is independent from the propulsion subsystem. The next step is to select which technology better adapts to the mission requirements. Although the cold gas and the propellant systems are chemical propulsion, they do not fit well. The best option is to use monopropellant thrusters, which has an adequate thrust range and a specific impulse, and do not have an excessive volume and mass. The propellant selected is the green monopropellant AF-M315E, that, compared with the conventional hydrazine, is not harmful at all. In addition, it is a 50% denser and has better performance. However, it requires higher power for heating the catalyzer. The thruster selected is the MPS 130 from Aerojet Rocketdyne. 2 of these thrusters are going to be included in the spacecraft, so the total 8 newtons can be reached. 4 newtons each of the systems. Its main advantage is small size, only 1 U. Finally, as all the propellant mass cannot be carried within the thruster systems, 2 additional tanks of 1 U each made of titanium has been included.
Hello, my name is Lucas, and now there will be discussed the ADCS subsystem, which is in charge of the attitude determination and control by means of a set of sensors and actuators. So the path to be followed will treat the control modes, the disturbing environment, and the reasons behind the selection of the control system. The control modes, which are based on the mission requirements, can be divided into two main blocks. The first one, the initialization phase, and then the modes that will be used along the mission, such as the contingency or safe mode, the science, data transmission, or even the sleep mode. Then, and in terms of the disturbing environment, there must be evaluated the disturbing torques that come from the atmospheric drag, the solar radiation, the magnetic field, and the gravity gradient. All in all, the most important ones have resulted to be the atmospheric drag and the magnetic field influence, due to the low perigee altitude of the orbits. Nonetheless, and as the satellite reaches farther distance from the Earth, there will be needed a further evaluation of the disturbing torques. At the end, and in order to be able to balance the disturbing environment, there is needed to define the components of the ADCS system. There has been selected an active control technique, aiming for greater accuracy and avoiding the spinner configuration, based on 3-axis stabilization and a zero momentum system. This selection has been highly influenced by the payload pointing requirements. So, in terms of sensors and actuators, it has been decided to implement 3 reaction wheels, torque rods to perform the saturation, and in case there will be needed external aid, it will be able to interact with the thrusters. Sensors will be composed by an AMU, a star tracker, a magnetometer, and 2 sun sensors, so that at the end the total system is able to provide the required pointing accuracy of lower than 0.1 degrees.
Hi, my name is Javier, and the communication subsystem has to send and receive the telemetry data and send back to Earth the payload data, which is the main objective of the mission. The main driver of the communication subsystem is the frequency, and choosing it is choosing the band in which we will be working. The frequency affects the free space and atmospheric losses in a bad way, the antenna size in a positive way, and the power transmitted also in a positive way. From the modulation possibilities, we will choose phase shift keying. We can send a different number of bits per symbol. This increases the efficiency, but also increases the bit error rate. With the maximum bit error rate, we choose that the best option is to use a QPS key with 80% code rate, which gives an energy-to-noise ratio of 3.4 decibels. To cite the linear equation, some assumptions have to be made, as for example, the antenna efficiency that is set to 0.6, or the maximum elevation that is set to 30 degrees, which increases the propagation losses through the atmosphere. The pointing in the antenna is considered the worst possible, which is pointing at the edge of core rate. This gives a loss in the antenna of 3 decibels. The most important parameter is the bit rate. We have set it to 350 bits per second, which allows us to send the payload data in 4 days. Taking into account that the travel back to Earth takes 7 days, we have 3 days to avoid a risk of failure in the final part of the mission. With this bit rate, we have also an extra of 0.8 megabytes that we can use to send telemetry data every day. With all these, 2 options are analyzed, one using the X-band and one using the S-band. The winner for us is the S-band, not because it has a lower power transmitted, which is the X-band, but it has a lower enough power transmitted, it is cheaper, and it has a higher half-beam width angle, which is desirable for us. It will be using a total amount of 0.19 watts. The electric power subsystem will be solar-based, therefore both solar arrays and batteries will have to be sized. The sizing has to be done with the requirements for each of the subsystems. We have a total amount of 26 watts as nominal requirement for power and a peak power of 84 watts. The solar arrays obtain power while in sun, and they have to store enough energy for the eclipse. We will size them for nominal conditions. These are a risk, but taking into account that we have batteries, we can use them for peak conditions. In the eclipse, the ADCS and the payload will be active, and we can allow also for 1 barn. The technology selected will be the one that gives the higher efficiency. Making some assumptions for the efficiencies and using a pointing error of 30 degrees because the pointing will be done with the whole spacecraft, we obtain that we need 35 watts. With the commercial off-the-shelf databases, we obtain a solar array that gives 37.41 watts with 800 centimeters squared. For the lithium-ion batteries, taking into account that the duration of the mission will be less than 1 month, we can assume that less than 1,000 cycles will perform, and therefore we can have an 80% of depth of discharge. With this, we can use a battery that has a capacity of 45.4 watts-hour. With this battery, if we reach peak conditions, we would only drain a 3.6% of it.
The mechanical and structural subsystem will be presented evaluating the overall mass of the spacecraft. Then there will be assessed the arrangement of the components, which will impact the center of gravity, and finally there will be mentioned the mechanism on the structure. Once all the components have been set, they must be divided into inner and outer components. Also, certain margins have to be defined depending on the maturity level of the technology. All in all, the final mass of the spacecraft will be around 14 kilos, needing a 8 units platform. Here it is presented the look of the satellite by means of its external shape, where you can locate a 8 units structure, a communication antenna, and finally the 8U deployable solar arrays. In terms of the internal components, there can be spotted the payload and the spectrometer, the ADCS system, the thrusters and the fuel tanks, and finally the battery. In the case there is performed a mass decomposition per subsystem, the heaviest one will be the propulsive, followed by the structural, the ADCS, and the payload. Additional remarks comprise that the payload and the communication are located in the same phase, also the solar arrays on the opposite face of the payload. In this way, we avoid direct pointing of the camera to the sun, and finally a diagonal thruster configuration. So all in all, the center of gravity will be located with a low deviation from the middle point of the structure, which will be around 1.3 centimeters. In terms of the mechanism, two main groups can be found. The first of them will be the solar array deployment, which will use a hinge and torsion spring. It is also important to compute the fundamental frequency of this mechanism. Moreover, the launcher attachment is also important, being selected a 12-unit dispenser for the proposed geometry and providing the main interface and protection to the structure.
Hello, my name is César and I'm the engineer in charge of developing a thermal subsystem. First, we will underline the main steps that ought to be followed in order to develop this thermal subsystem. In this flowchart, we have remarked on the main boxes that will be explained along the following slides. Despite the fact that the mission has already been explained, from the thermal point of view, it is interesting and necessary to identify which are the hottest and the coldest point of the overall mission. First, the hottest point is thought to happen in the sunlit orbit around the Earth. This is because the spacecraft will receive the infrared emission from the Earth, the albedo, and the heat flux from the Sun. Whereas the coldest point is either happening in the eclipse part of this orbit or in the flyby around the Moon. Nevertheless, the flyby is performed at such a high speed so that the eclipse lasts so little as to have any influence on the temperature of the spacecraft. Then we'll go along with this hottest point and this coldest point. Once the most extreme points have been identified, it is necessary to define which are the operational and survival temperature requirements of each of the components that form the spacecraft. Here we have gathered the typical temperature range requirements, but since in the end we have used commercial off-the-shelf components to develop our satellite, these temperature requirements may vary. For example, in the case of the battery, the temperature requirement goes from -30 to 80 degrees Celsius, and in the case of the spectrometer, it varies between -20 and 40 degrees Celsius for the operating range. Then we would have to develop what is called the thermal model, which is a simplification of the proposal of the structural engineer. Here we can see represented the different components, and we have summarized the material they are made of and the optical properties. It is important to underline that the outer box has been painted with a mixture of black and white temperature in order to guarantee the temperature requirements are satisfied, and also the first simulations yielded that the fuel tank was operating at the lowest temperature as to guarantee the safe operation, so we had to include what is called a multi-layer insulator that appears green colored. Finally, by means of the use of SATAM software, we have developed the simulation of 4 different orbits around the Earth and a simulation of the flyby around the Moon. Here we include the first orbit simulation because it is the most interesting one from the thermal point of view. We can see in this plot how the temperature requirements are all satisfied for all the components, and we need to pay specific attention to the payload, the camera and the spectrometer, and we see that they satisfy the temperature requirements because they are always between 18 degrees Celsius and 21 degrees Celsius.
Just to briefly mention that the management of the project has been embraced by the concurrent engineering methodology in order to optimize the final result of the project. Moreover, some management plans have been developed to do so, such as the work breakdown structure, the Gantt chart, a bottom-up cost estimation, and a risk analysis. Thank you very much for your time and attention. This has been all from our side, and in case that you require any further clarification, please refer to the document.